Process Safety, Module 2, Scaling Up by Denis Pratt, Sanofi. After attending this presentation, you should be able to design safe scale-up experiments, understand the conclusions of basic calorimetric experiments, be aware of the thermal risk and the pressure risk of chemical reactions, and carry out safely hazardous operations. Before listening to this module, I recommend you to attend Module 1, dedicated to screening experiments. It gives notions of hazards and risks, presents the hazards linked with materials and operations, shows the most hazardous chemical groups, and presents briefly the differential scanning calorimetry. In Module 2, we will make reference to reaction calorimetry. This technique is presented in Module 3. Scaling up. The risks are not the same on the gram scale than on the kilogram scale and beyond. If a reaction works on the gram scale, how to conduct it safely in the kilo lab or in the pilot plant. First of all, before a scale up, try to eliminate some hazards by substitution of undesirable solvents, for example. See the training package on green solvents. Optimize the process and check its reliability. A robust process is generally safe. Determine the fate of reagents in excess. They might give hazardous side reactions downstream. Avoid scale-up factors higher than 100. Intermediate scale-up permits to better detect exothermic phenomena or delayed reactions or crystallizations. Before a scale-up in the kilo lab or the pilot plant, a good practice is to make the last experiment in the lab using 50 to 100 grams of noble material. Observation is key, and this scale is well adapted to detect any abnormality. Avoid to isolate the product by concentration to dryness. Crystallization is more reproducible and less hazardous. There are several prerequisites for any scale-up. First of all, identify the actual stoichiometry and the byproducts and equilibrate the reaction equations. You need a clear, detailed laboratory procedure with a simple and reproducible in-process control. You need to identify all hazards, those linked to the materials and solvents, those linked to the instability of the different phases of the process, the hazards of the reaction itself, and the hazard of each operation. You need to know perfectly the equipment train in which a scale-up will be conducted, especially if you run the experiment yourself. A good way to learn is to clean it with the reaction solvent at reflux and test all the functions you will need. And you must carry out a risk analysis on each process operation and to establish practical safety barriers to reduce the risk. The equilibrated equations are written with the actual stoichiometry. One must identify the fate of each element and try not to forget anything. Here, an acyl chloride is formed with 1.3 equivalent of thionyl chloride in toluene. 1 equivalent of SO2 and HCl are formed, thus an alkaline scrubber is needed to give eventually sodium chloride and sodium sulfite. 0.3 equivalent of thionyl chloride remains with the acyl chloride. Concentration in vacuo is needed to eliminate it together with some toluene. This means that thionyl chloride will be condensed in the pump trap, which generates an occupational risk. Then the amide is formed by addition of a slight excess of amine. As HCl is formed, excess amine can be eliminated by a simple aqueous wash as a hydrochloride salt. In conclusion, the drawing of this scheme highlights all the chemical issues and gives clues to solve them. Identification of hazards. The health hazards can be drawn from the safety datasheets, in particular for reagents and solvents. You need to identify which personal protective equipment are necessary, if they are available in the lab, and if they are in good condition. The environment hazards are not relevant in the pilot plant. Just ban solvents which are hazardous for the ozone layer. The main process hazard is the formation of explosive atmosphere, ATEX, especially with solvents. But hazards can also arise from unstable reaction mixture, reagents, wet and isolated products. Products can decompose during drying, mill, and even storage. In Module 1, I explained how DSC detects such behavior. Incompatibility between materials is a frequent cause of accident. An incompatibility matrix is needed. Uncontrolled reactions must be avoided. They can result in gas evolution, over-evolution, pressure buildup, or decomposition. Calorimetric experiments are a good way to prevent them, as explained in Module 3. Fire hazard. Fire is the result of ignition of a mixture of a solvent, vapor, and air above the flash point of the solvent and between the lower limit of explosion and the upper limit. If the process is run 10 degrees below the flash point, there is no risk, but in most cases the process temperature is above the flash point. Be careful of solvent vapors in water phases, they can be ignited. Inside the reactors and tanks, in order to avoid the attacks, oxygen is displaced by blanketing with nitrogen or argon in some cases. With less than 5% of oxygen, there is no ignition risk. For solvent drums or open vessels, no blanketing is possible. In this case, ventilation is applied in order to decrease the percentage of solvent vapor below the lower limit of explosion. This is very effective to get a safe transfer process. This can be achieved with a flexible hose placed on the drum. In the lab, one considers that under the fume hood, there is no significant attacks risk. The third way to limit the risk is to avoid the ignition sources. Of course, one can ban flames and avoid electric sparks with an equipment conform to the attack zoning, but one cannot be 100% sure that all sources of electrostatic discharge will be avoided. Incompatibility matrix. The incompatibility matrix permits us to detect interactions with other materials. Of course, there are always incompatibilities because the chemical reaction consists of reacting together a reactant and a reagent. But what is important here are the undesired interactions. List all materials in the first column. In the second column, list the possible reaction with the other materials, and then with water, the cooling fluid in the condenser, and the equipment material. You can use color codes to highlight the hazardous phenomena. In this case, for example, the reaction must be run in a glass-lined reactor, and the condenser must be empty or filled with an inert fluid such as toluene. As a chemist, the first process hazard you have in mind is the runaway, when the reaction is no more under control and the mixture starts to decompose. The decomposition energy is circa 10 times higher than the reaction itself. It is relatively rare but quite dangerous. There is also the risk of overpressure, which can result in the pneumatic explosion of the equipment. It can be due to an endothermic reaction, which releases rapidly gases, such as the acyl chloride formation. It can also result from a very exothermic and sudden reaction with solvent over-ebullition, like during the formation of a Grignard reagent. The safety barriers for these events are pressure relief valves or bursting discs, and ideally the vent is directed to a catch tank. The material can also decompose during milling as a result of the friction energy. And if the product is unstable, it can even decompose on drying. To answer the question, is the chemical reaction safe? Calorimetric studies are needed. These studies aim at acquiring knowledge on the desired reaction, but also on the undesired decomposition. For the desired reaction calorimetry is carried out in an isothermal mode. The reaction heat flow, the energy are measured, the maximal temperature increase is calculated, and the gas flow can also be measured. For the decomposition, one estimates the stability limits by differential scanning calorimetry with a temperature gradient. The decomposition energy is also measured. In a reaction calorimeter, the reaction is carried out like it will be in the kilolab or pilot plant. The heat exchange between the inside of the reactor and the double jacket fluid is measured continuously. Many parameters are measured or calculated. The most important ones are the maximal heat flow in watt per kilogram, the enthalpy of reaction in kilogram per mole, and the delta T adiabatic in degrees Celsius, the maximum increase of temperature in case of rapid addition of reagent together with cooling failure. In order to rank the reaction system, Francis Stossel has established a very simple system based on the comparison between three temperature values. The MTSR, maximum temperature of the studied reaction, which is the sum of the process temperature and the delta T adiabatic obtained by calorimetry. The boiling point of the reaction mixture, the temperature of decomposition, more exactly the temperature at which the reaction mixture would decompose after 24 hours. This value is estimated, for example, from the decomposition temperature by DSC with a safety margin of 100 degrees. Depending on the order of this temperature, the process criticality varies from 1, safest, to 5, most critical. Criticality 1 corresponds to a MTSR lower than the boiling point. The reaction can be exothermic, but without any risk of overebullition or decomposition. Note that reactions with gas evolution are endothermic, but may be hazardous. Pressure risk. Criticality 2 also corresponds to a safe reaction. MTSR is lower than the temperature of decomposition. The reaction may be strongly exothermic, but not enough to reach the decomposition. In this case, the ebullition does not constitute a safety barrier. Reactions ranked 3 are moderately safe. An uncontrolled reagent dosing can result in an overebullition, but not to a decomposition. Reactions run at reflux are generally ranked 3. Reactions ranked 4 are more risky. Here, after the overebullition, the reaction can start to decompose. The formation of Grignard reagents are in this category. In both cases, the reagent dosing must be under control. Reactions ranked 5 are the most hazardous. MTSR is higher than the temperature of decomposition. A rapid dosing of the reagent can lead to a decomposition of the reaction mixture. The solvent ebullition is no more a safety barrier. Some mixture of oxidizing agent and solvents are in this category, sometimes even at room temperature. If possible, the process must be modified. If not, deviation studies and multiple safety barriers are mandatory. The transfer from the lab to the kilolab or pilot plant must contain a risk analysis. The process is divided into elemental operations, and for each operation, the main risks are listed. It is often linked with ATEX or occupational health. Then, the safety measures are decided. Do not hesitate to give details. For instance, the charging of toluene generates an ATEX risk and an exposure risk by inhalation. To limit the risks, the equipment will be grounded to avoid electrostatic charges. A deep pipe will be used. A solvent will be charged under vacuum with a local extraction. The operator will protect himself with a cartridge mask, and in the vessel, vacuum will be broken with nitrogen to avoid the ATEX. As takeaway messages, I will insist on that the worst operating procedure consists of mixing reactants, reagents, and solvent at room temperature and heat up the mixture. It can work in the lab, but there is a high risk of delayed start and possibly uncontrolled exotherm on scale-up. For highly exothermic reactions, ranked 3 to 5, the reactant must be dosed with a pump very regularly and with a careful control of temperature. The temperature must be sufficiently high to avoid accumulation, but not too high in order to avoid overebullition or decomposition. It is mandatory to know the reaction criticality, but beware of oversimplifications. Endothermic reactions are of course thermally safe, but if the gas release is important, an overpressure hazard is generated. Concentration of the reaction mixture alters its stability and may change the hazard ranking. In general, we try to avoid the scale-up of reactions ranked 5, but it is not always possible. In such cases, specific measures are taken to limit the risk. Do not forget either that the chemical reaction is not always the most hazardous operation of the process. A reactant solution may be unstable even at room temperature. A quench may be very exothermic and may generate hazardous gases. Concentrated solution may also be unstable. When you concentrate solutions, hazardous gases and solvents can be trapped in the vacuum pumps. Operations like grinding or jet milling are very energetic and can induce decompositions. Specific powder safety studies are recommended. Also, a risk analysis is needed for any scale-up and must be updated regularly. Minor changes may have major safety impacts, and the larger the scale, the higher the risk is. Big scale, big risk. This is why you must ban scale-up factors above 100. On the industrial scale, the risk analysis of the current process is not enough. We also need to analyze the risk of all possible deviations.